All right, this is 10.9 real gases. Okay, before we were talking about ideal gases, and ideal gases are hypothetical, where no gas exactly follows the ideal gas law actually. Okay, but the ideal gas law deals with those 5 assumptions from the kinetic and molecular theory. So about gases not taking up any space and no real attractions and things like that. So those are ideal behaviors. Okay. But actually, in real life, okay, you're going to look at, so now we're going to examine the experimentally observed behavior of real gases by measuring the pressure, volume, and temperature and number of moles for a gas and noting how the ideal gas law depends on pressure and how ideal gas laws and real gas laws are different and when they kind of behave the same and when they don't behave the same. So if you look at the 2 graphs you have, and yours are a little bit clearer than mine, okay? If you look at the one on the left, okay, if you see the straight line across, or straight dotted line across, that is my ideal gas behavior, okay? So as the pressure changes there, okay, PV over RT is going to stay in V1. And what we'll notice about these 4 different gases, okay, is that we have times when they are really close to the ideal gas and times when these gases don't act like the ideal gas, okay. And down here are the times when they really act more like an ideal gas, okay. And up here, they're not really acting much. So here, this is where they are closer to being ideal. Now, if we do the same sort of thing on the right side here, okay, with your pressure, and my pressure changing in PV over T, what we notice is now the temperatures are different up here on the right. And at a higher temperature, yours says 1,000 Kelvin, that is the closest to my ideal gas kind of line, what an ideal gas would behave like. So what we get out of this, okay, is that at lower pressures, and at higher temperatures, a real gas and an ideal gas are pretty much interchangeable. But once we get to low temperatures and high pressures, you're no longer really acting like an ideal gas. So here we're looking at lower pressures and higher temperatures is when we're closer to an ideal gas, and that is what you have to fill in there. It says, note from the graphs above, the behavior of the gas appears to become more nearly ideal as the temperature is increased and the pressure is decreased. So how can we modify the assumptions of the kinetic molecular theory to fit the behavior of a real gas? And a guy named Johann van der Waals went to work on this problem, and he eventually received the Nobel Prize. And this is what we're going to look at with these kind of assumptions for the kinetic molecular theory and how that changes with a real gas. So the first assumption we're going to look at here for the kinetic molecular theory, and one we're kind of going to fix a little bit, is going to be where an ideal gas consists of voluminous particles that don't interact. But real gases have finite volumes, meaning they have a volume, and they take up space. Okay, same thing. They have a volume, they take up space. All right, therefore, actual container volume is less than in the ideal gas law. Because when we look at these gas particles, okay, they actually do take up space, even if they are far apart. So that means in real life, the volume of this container is really less because these particles are taking up some of that overall space. So what we do is we correct for that, and we have normally PV equals nRT, but now we're going to take and we're going to correct my volume. And so we take P times V minus NB equals nRT. And N is still the moles, but B is a constant for a certain compound. Okay? And this whole thing here is my correction factor. And the reason it's N times B, B is kind of like how much space that particular gas compound takes up, and N is how many moles. Well, if you have more moles, you're going to have even less of a volume. If you have less moles, you're going to have more of a volume. So it depends on how much I have. Okay. Now the second assumption here that we're going to look at deals with that in an ideal gas. Okay, it says that they don't have any interaction, meaning they are not attracted to one another and they aren't repelled from one another. Well, what I do know about an actual gas, okay, or a real gas, is that they do. So real gas particles are attracted to each other. Okay, since they are attracted to each other, they hit the side of the container with less pressure. And how that works, okay, and you have a little picture on yours, okay, where I have a container and I have these gas particles. Whereas this gas particle tries to hit the container wall, okay, it is also attracted to these three gas particles around it. So since it's trying to kind of get pulled to the right here with these particles, it's not going to hit the left side of the container with as much pressure or force, because it's not going to be moving as fast, because it's not like it's freely moving around. It's kind of attracted to the right side a little bit. So it's going to be a little bit lower than what you would think. Okay. Now, the higher the concentration, the lower the pressure. And so we have a correction factor for that. PV equals nRT. So my observed pressure, okay, is the actual ideal pressure minus my constant for that compound, and N over V squared. N over V is my molarity, concentration, I said. A is the constant for a compound, but it's not the same as B. Okay, so what we end up with for an overall van der Waals equation, you want to write this somewhere down bottom, is P plus A times N over V squared times V minus N times B equals nRT. It's still PV equals nRT. You just have now this correction factor and this correction factor. One for volume, for the amount of space particles take up, and one for the fact that they are attracted to one another. Okay? So then the last thing is, why does the van der Waals equation work? Okay? Meaning, why do you need it at high pressure and low temperature? Okay? Well, if you have a low pressure, that means I have a large volume. Well, if I have a large volume, that means then that the volume of my container is large compared with the volume of the gas particles. So that means that the volume of my container is pretty much equal to the volume that's available. Particles are so spread out because my volume is so big. The amount of space that those particles actually take up really isn't that much compared to the overall. Okay? But if I have a high pressure, that means I'm really probably going to have a smaller volume. So the comparative amount of space that those particles take up is really, really big. Okay? So look at it this way. A larger container, smaller container. If I have 5 gas particles here, and the same ones here, now they're about the same size, and notice how this space that these particles take up is way more part of the issue here, okay, than here. Because in the one on the left, I have so much more real space here for them to move around. The space that they take up really isn't that much. All right. The second reason that it works here deals with at high temperature. At high temperature, my gas particles are moving very quickly. If they're moving very rapidly, the particles really don't interact that much. Since they are moving so quickly, now they don't have time to interact with one another, which means then that my particle interactions really aren't a big factor anymore. But if they're moving slower, which is a lower temperature, now they've got more time to kind of stick together, which is going to mess up my pressure. Okay? So let's look at a couple of practice problems with this van der Waals equation. And this is on your green sheet if you ever forget it. Okay. It says if 1 mole of an ideal gas is confined to a 22.41 liter at 0 degrees Celsius, it would exert 1 atmosphere. Use the van der Waals equation and the constant in the table to estimate the pressure exerted by 1 mole of Cl2 in 22.41 liters at 0 degrees Celsius. So if I were to use this ideally, I get 1 atmosphere. So we're going to compare what we would get out of the van der Waals to 1. And notice there at the bottom of the page are all of those constants. So let's start out with my equation. It's going to have P plus A times N over V squared times V minus N times B equals nRT. Let's go ahead and we plug everything in. Pressure, which I don't know, plus my A. So for Cl2 on the table, and I'll tell you that my A for Cl2 is 6.49 times my moles. I have 1 mole. My volume, they tell me, is 22.41 liters. I'm going to square it times my volume again, which is going to be 22.41 liters minus 1, because I have 1 mole, times my B. I find B for Cl2, which is 0.0562. And then I get equals N, which is 1 again, R, which is still the same, R, 0.08206, and we're going to have room there, but then my temperature is going to be 273. So you have to do a little bit of algebra, okay? Do one thing at a time. So we kind of get all that math numbers, get all that math, do all that math, plug your numbers in. Pressure plus, when we do this math here with the 6.49, I'm going to get 0.0129. I'm going to take this times when I do the math of 22.4 liters, which is going to be 22.35. And the right side's all going to equal 22.41. Now I'm going to, I personally like to distribute, so I'm going to get 22.35 pressure plus 0.02883 equals 22.41. Subtract and divide, my pressure is 0.9898 atm. Notice how that is very close to the ideal gas law that gave me an answer of 1. But it's a little bit lower. My van der Waals is correcting for that. Okay, go ahead and try the last problem. Okay, so here you should get 7.47 atm when you're looking at letter A, dealing with the ideal gas law. When looking at B with the van der Waals equation, you should get 7.18 atm. And again, notice how they are just a little bit different. But again, the further you get from being like an ideal gas, the further apart these two will get.